Hi everyone. I'm very happy to share my recent result on succinct blind quantum computation using random oracle. I'm Jia Zhang from Boston University. So what is blind quantum computation? In this problem, Alice has a quantum circuit C, and he wants to evaluate it and get C0. But he doesn't have the ability to apply C itself, so it makes use of a remote quantum server. But on the other hand, it doesn't trust the server and want to keep this secret. So it wants to design a protocol to interact with the server and get the result in the end. This is a fundamental problem in quantum cryptography. On the one hand, the problem itself is very important, because with high probability, in the near future, quantum computers can only be used as a cloud service. So if we want to make use of its power and simultaneously want to keep our data or circuit secure, such a protocol is needed. What's more, the study of these problems has often led to new techniques that can be later applied on related problems, like quantum computer verification. There are three minimum requirements for this problem: query, security, and efficiency. For security, we use indistinguishability-based security, which means any malicious servers could not distinguish whether a client is using the real circuit C as the input, or is just using the auxiliary stream. So these are just minimum requirements, and there are still many different settings. In this work, we give a new universal blind quantum computation protocol, where the client-side quantum computation is succinct, which means it's at most a fixed polynomial, the security parameter, and is secure in the quantum random oracle model. So let's give a review of existing works. And we focus on universal protocols using only a single quantum solver. One class of protocols is IT secure protocols. And the representative is the ubiquitous protocol by Broad, Fishman, and Carterfield 10 years ago. In this protocol, the size of quantum gadgets is linear to the size of the circuit to be evaluated. Another class of protocols are protocols based on public encryption. An early representative is a protocol by Schaffner and Spielman. And recently, Hardy built a protocol based on the learning with error assumptions. In this protocol, the client can be completely classical. And we focus on assumptions and wonder whether the secret complexity can change under different assumptions. And the following question: what if we have only symmetric cryptographic primitives? Later, we will model symmetric primitives as a random oracle. And we also have a specific goal. We want our client-side quantum computation to be independent to the circuit side C, which means we want it to be better than the existing IT-secure protocols. So if we classify protocols based on client-side quantum computation and assumptions, we get the following table. This table shows different trade-offs between client-side quantum computation and assumptions. So existing work shows the trade-off under IT-secure setting and the with error-based setting. So our work shows a new trade-off in the quantum random oracle setting, which reveals a more complete cryptographic picture for this problem. So our protocol is as follows. First is correct and efficient, and there are two phases. In the first phase, the client will send some quantum gadget to the server, which can be prepared using only polycappa gates. And in the second phase, both parties do some classic interactions. And it's secure in the quantum random oracle model. What is the quantum random oracle model? The quantum random oracle model is raised in this paper as a quantum generalization of the classic random oracle model. In this setting, there is an oracle which encodes a random mapping. Other parties can curate this oracle. This can be seen as the ideal model for head functions or symmetric encryption. In the formal setting, we can design protocols in this setting, improve the security. And in practice, we instantiate the random oracle with hash functions or block cipher. But there do exist some extensible constructions. So the instantiation can be subtle. But on the other hand, QROM and ROM have been extensively studied in many problems and provide only known construction of many cryptographic protocols. So the technical part is as follows. First, we give an overview of protocol construction. Then we show the technique for each step in the protocol construction. The gadgets that we will use is as follows. The client will hold 2 different keys, which are 2 different long strings. And the adversary will hold the superposition of these 2 keys. So this kind of gadget is used previously by many papers, so it's not part of our innovation. One observation is, with only the superposition of these 2 strings, the adversary can only output the concatenation of these 2 strings with very small norm. Later, we will generalize this observation to some weak cases and introduce the asset security. So top-down overview is as follows. First, the client will send some initial gadget to the server, which only contains polycard packets. And each gadget is of the following form, but the keys are different. Then both parties use some classical interactions to expand the number of gadgets to a large number of gadgets. And these gadgets will have some kind of security. And finally, both parties can use this gadget to evaluate the circuit security. The first step is called the remote gadget preparation, and it's further achieved using the following idea. First, we design weakly secure gadget increasing protocol, then amplify the security. So this step is the most difficult step, and this step is not trivial. A very informal illustration is as follows. We can imagine in the beginning, the server holds some initial gadget that is fully secure. And this gadget will go through some gadget generation protocols. And the number of gadgets will get increased, but the security will get decreased. And they will go through some amplification process, which improves the security at the cost of decreasing the number of gadgets. And we emphasize that this is only a very informal illustration because the gadget generation and security amplification are actually not two separate protocols that can be executed alternatively. What we actually do is to take the gadget generation protocol as a sub-protocol and use security amplification to amplify it to an upper-level protocol that is fully secure. So what we need to do later is first, we need to design modular framework for sub-protocol design. We will formalize the remote gadget preparation concept and define the security. The security contains the following steps. We first give the notion of asset security of a state. Then based on this concept, we design the normal security and weak security of a protocol, which will be the framework for protocol design. And for each protocol design, we need to strike balance between different parameters like awareness and security. So what is remote gadget preparation? The awareness means the preparation protocol transforms any input gadget to L output gadgets. And we want it to be gadget increasing, which means L over N is bigger than 1. The difficult part is the security. We use the notion as security, and we first define the security on a state. And we can imagine the state of other parties can be described by a purified joint state. The randomness are purified by the environment. And the security definition is as follows. So the gray color part is also very important, but we want to focus on the most basic things. So intuitively, we say the state is 2 to the eta A as secure for some key pair K. If any adversary with less than 2 to the eta Q to the random oracle could not output both keys in K with norm bigger than A. Which means the adversary's ability to output both keys from the state is bounded. So based on this notion, we can define the security of a protocol. The security of a protocol means the output state of this protocol have as security for each of the output keys, and the security should be exponentially good. But this definition is not enough for our protocol design because the protocols appear in our work are mainly weakly secure. The weak security can be formalized as follows. It also uses as security, but we have a better control on the behavior of the protocols. The protocols have 5 parameters. 2 of them characterize the input security, and 3 of them characterize the output part. It says, if the input satisfies some kind of security, described by the first 2 parameters, eta and c, then the output part will have the following properties. Either the adversary can only pass the protocols with some small probabilities, or the output part of the pattern space should have some security, described by eta prime c prime. So because here p might be close to 1, but there is at least an inverse polynomial gap. So these 2 cases should not be merged, at least in the first several sub-protocols in our paper. So let's go to the technical details. We will first construct a weakly secure engaging equation protocol to amplify it to a fully secure one. So the basic goal is as follows. We want to generate 2 gadgets from 1 input gadget. We want the output part has some weak security. So this is the quantum mappings, and it can be achieved using a classical primitives called reversible lookup tables or reversible couple tables in some previous works. So in this work, what we need from these lookup tables are string-to-string mappings. They do not carry computation directly. So we also rename it to reversible lookup tables. But this is not easy to do directly because the reversible lookup tables requires the input number and the output number to be the same for the reversibility. But if we simply use the lookup tables on these mappings, it's not possible to implement this mapping securely. So the key idea is to introduce a bitwise permutation on the output part, and first seek for transformation from this 1 input gadget to the bitwise permuted version of the output gadgets. And this permutation is sampled by the client and kept secret by the server to the server in the beginning. So the server holds 2 gadgets, but the bit positions are permuted secretly. And then the client will use some way to review the permutation to allow the server to depermute the output and get the result. So there seems to be a dilemma here. We want to keep pump secret to preserve security in the first step, but the client still needs to review the permutation in the end to allow the honest server to implement the mapping. And this leads to the following idea. When we introduce a helper gadget, instead of seek for the transformation from this one gadget to permitted two gadgets. We seek for this mapping with this additional helper gadget. And after we implement this mapping, the helper gadget will go to a Petty-Harman test. This is a Petty variant of the Harman test in this paper. Intuitively, the property that we need is a property called proof and predictability, which means if the server want to pass this test with high probability, it loses the ability to predict keys from the post-test state. So the Petty-Harman test gives us some control on the adversary's behavior after the test. And now the overall protocol goes as follows. Both parties first use this mapping. We first implement the mapping, the first step. Then both parties will do a Petty-Harman test on the helper gadget. And conditioned on the test passes, the client will reveal the permutation to the server and allow the server to depermute. And our observation is at each time step, either the bitwise permutation or the keys in the helper gadget is hidden from the adversary. And this will help to protect the security of the mapping in the first step and in the whole protocol. So now we can go to the implementation of the first step. We will try to seek for a reversible lookup, reversible encoding for this step. There are still many issues in this encoding, but this issue can be solved. One issue is this mapping is a mapping from 2 gadget to 3 gadget. So the input and output numbers are not compatible. And this can be solved by paired one key pairs on the input part. And this key and in the protocol, the client can simply provide classical description of this actual key pair. And but this is still not enough. And we have one more idea, which is when we do this, we construct this reversible encoding of these mappings. We choose the underlying gate for Gabriel to be the top gate. So the reason is that in top gate, the 2 branches corresponding to B1 equal to 0 and B1 equal to 1 behave differently. And this B1 is a bit value as a helper gadget. And this gives us further control on the adversary's behavior. And it can be characterized by the property that we put called proof and testability. So we note that, so this is a construction that are formally defined in the paper. So another construction that is more succinct and intuitively equivalent is as follows, but the details are not formally verified yet. We can directly construct the reversible encoding of this one gadget to permitted 2 gadgets mapping. And there are 2 ways to distribute the components. One way which corresponds to the B1 equal to 0 case in the current in the current version, it encodes the mapping in a following form. And another way corresponds to the B1 equal to 1 case in the current form, which encodes the mapping in a different way. Then we can encrypt the B1 equal to 0 encoding under E0 and B1 equal to 1 encoding under A1, and send both decoding and send both encryption to the server. And server can use this information to evaluate the mapping securely. Details are not have not been formally verified yet, but intuitively it should also work. So we can have more intuitions for the protocol. We can provide two additional viewpoints to get informal intuitions. One is a classical adversary viewpoint, where we can analyze the protocols against semi-classical adversary. If we omit permutations, the semi-classical adversary can break many rows in the GAP table by decrypting back and forth, and further decrypt the security of the whole protocol, which tells us that permutation is actually quite important in our protocol. And we can also use this protocol from the Petty-Hammer test viewpoint. So there are two branches correspond to the helper gadget. And the behavior of the randomly, and the behavior of the reversible encoding behave differently these two branches. If the adversary want to behave maliciously, what it can do in these two branches are actually different. But these two branches does have an intersections, which is honest mapping. So honest behavior can always pass the protocol. But for a malicious adversary, its behavior on these two branches will, if you want to behave very maliciously, the behavior of the two branches will have some differences, which is further controlled by a property from the Petty-Hammer test. And the formal proof for the weak security takes the Petty-Hammer test viewpoint and technically merge some intuitions from the classical adversary viewpoint. I don't want to tell about the technical details into very, very detailed in this talk. So finally, we can return to our protocol. So we have constructed a protocol that transforms two gadgets, where one is a helper gadget, and one input gadget is a gadget for reversible encoding. And so this is still not gadget increasing, but we can, and the final observation is we can do a parallel repetition of these protocols, and the helper gadget can be shared. So the final protocol will transform n+1 gadget to 2n gadget, which is gadget increasing and still weakly secure. And the weak security of the output part is weaker than the security of the input gadget. So we generate more gadgets at the cost of decreasing the security. Now we go to the amplification, and the technique is called the repeat and combine technique. So to understand the definition, to understand the technique, we can first go back to the definition of weak security. So this is the protocol level definition, and we focus on the source weakness on the output part. So to make it fully secure, first we need to remove the first case. We want P to be exponentially small, which means the first case can be removed and merged to the second case. And in the second case, the source weakness is on C prime. If C prime is exponentially small, then this will become a fully secure protocols. But C prime is not necessarily exponentially small. So we will solve the first problem by repeat technique, and solve the second problem combine technique. Repeat technique is relatively simple. In this technique, we use a parallel repetition-based procedure to further improve the security. So previously, we already have a sub protocols for weakly secure gadget generation. And we do many such protocols in parallel on different blocks of gadget, and require that the server should pass on all the different blocks of sub-protocols. And this will improve the security and remove the P parameter from the weak security definition. But this is still not enough to improve the security to exponentially secure, to be exponentially secure. And to make it exponentially secure, what we need to use is a combine technique. So the basic routine is as follows. Let's imagine initially the server will hold 2 gadgets, which is in the malicious setting weakly secure. And we want to combine them to get a fully secure, to get a combined gadget with better security. And the client can allow the server to measure the XOR of the bit value of these 2 gadgets. And this will collapse these 2 gadgets into a single combined gadget. And the keys of the output gadget will be the concatenation of the 2 input gadgets. And the client can compute both combined keys using the initial keys and the server's measurement result. In the dream world, we want the security of the combined keys to be the multiplication of the security from the original keys. And if this works, the client can simply combine many gadgets, for example, kappa gadgets, and the security will have an exponential decay, which makes the protocol exponentially secure. But the story is not that simple. There's no free lunch in this protocol in the world. And the problem is the gadgets can be correlated, and security can be correlated. So we want to design our combined technique more carefully. What we want to do is to first design the time order of gadget generation application more carefully, and then we introduce an addition layer called security reflection layer. And the upper level construction of our combined technique is actually as follows. First, we take the sub-protocols coming from the repeat technique. Then we run it on many different blocks, which has kappa blocks. Then we first run the sub-protocols on the first 2 blocks and combine them. But by this time, the protocols on the remaining block haven't been run, and it will only be run after the combination of the first 2 blocks have been completed. And we note that the initial keys are actually decorrelated because which is guaranteed by the definition of the IC security, or the normal security. And if we combine these gadgets one by one and produce these actual gadgets on the fly instead of produce everything in the beginning, this will decorrelate the new gadget to some extent. Because, but that's still not enough. So we need to introduce an actual layer called security reflection layer. And every time we generate new gadgets from some sub-protocols, we will introduce some small number of virtually secure gadgets and use them to reflect the security of this newly generated gadget before the combination. And this will further strengthen security and help to decorrelate each gadget. The idea in the intuition setting for the security reference layer is as follows. Let's imagine the server randomly holds a gadget, and the security of this gadget is guaranteed by secrecy of K. And we can consider the following setting. We imagine that although currently K is protected securely to the server, but it might be made insecure by later protocols. So currently we want a way to switch the guarantee on the security to some other freshly new keys to make the gadget secure, even if K is revealed later. And the protocol is the basic routine is as follows. The client will introduce some freshly secure gadget, which is not used in the previous protocols. Then the client can send a lookup table, which encodes the mapping from the initial gadget and this new gadget to an output gadget. So there's no reversibility here. And different bit values on the initial gadget correspond to different bit values on the output part, but different bit values of the freshly secure gadget correspond to the same value on the output part. And after the server implements this mapping by decrypting the lookup table, the new gadget will be sealed into the petty harmon test, and the server will lose the predictability for these keys. The intuition is after this process, the security of the combined gadget will somewhat rely on the unpredictability of the freshly secure gadget. So it's not only on the security of the initial gadget. And then this basic routine can be applied on many keys simultaneously in parallel. And we can introduce many fairly secure gadgets to make the protocol exponentially secure. And proving the property of these protocols formally requires some technical proofs, which can be found in our paper. And the final problem is the combined technique actually consumes too many gadgets. Recall that weakly scaled protocols allow us to asymptotically double the number of gadgets, but combined gadget decrease the number by a factor of kappa, which makes the upper protocol gadget decreasing instead of gadget increasing. But this can also be solved. The solution is, before we do the repeat and combine amplification, we can first self-compose the underlying weakly scaled protocols for log kappa times, which will boost the gadget dependent ratio to theta tilde kappa. And on the other hand, in the combined technique, we only need to combine square root kappa gadget instead of combine kappa gadget. In this way, we can get a protocol that is both secure and gadget increasing. So let's give a glimpse of the security proof techniques. The framework is the security on the state and the weak security of the protocols. And an additional property that we need to consider is the well-behaving of the states, which is informally require the state to be able to be prepared using a linear sum of states of a limited number of random error curates. So we don't want the state to be something like the XOR or the random error contents, which is too ill-behaved. And one technical lemma that we will frequently use is state decomposition lemmas, which in my opinion is fundamental for the random error and might be useful in other settings. The motivation is to find a bridge from weak security to full security. In these lemmas, we show that intuitively any weakly secure state can be written as a sum of an exponentially scale state and a state with bounded norm, which can be seen in the most basic settings, but formal proof for this lemma is highly non-trivial. The formal proof uses an iterated convergent decompositions, and we note that these two states in the decomposition is not guaranteed to be orthogonal. The example is as follows. Initially, we can imagine the initial state has some level of unpredictability for x, where x is a string kept secret by the client. But the security is weak because the adversary might compute x with norm 1/10, for example. And this lemma says we can always write this state as a linear sum of two states, where the first state is exponentially secure for x, and the second state has bounded norm, which is constantly bigger than 1/10, but is still much less than 1. So finally, we can give a reduction from Lagrange preparation to universal blind quantum computation. This can be achieved in multiple ways. The concept is called the gadget CT8 basic factory, which transforms the superposition gadget to single qubit gadget, which can be used as building block of BFK protocol. So because the setting in our paper is slightly different from the existing works for 8 basic factory, the existing technique doesn't apply it immediately. And we need to go through some further steps, which is a little bit technical. But we can explain the protocol intuitively by assuming the initial state is honest, which is not guaranteed in the formal setting. For the transformation, we use the phase table, which encodes the mapping from y0 to a random string, and from y1 to the random string plus some less significant bits in the angle that we want. And this will allow the solver to add additional phase angle to this gadget. Finally, we can use the Hammer measurement technique from Marty's paper to collapse the set into a single qubit gadget. And finally, we run BFK to complete construction. So, as a summary, we give a new universal blind quantum computation protocols where the client-side quantum computation is polynomial of kappa. It's a fixed polynomial, and it's secure in the quantum random oracle model. So that's some more questions. I think a very important question is to give further understanding on this table. There are still many unknown cells. And for the top left corner, we only have some negative evidences, but evidence can still be improved. It's not strong enough. So thank you for listening.